Okay, in this lesson we're going to look at continue our work on finding particular solutions using or particular solutions to differential equations, and this is an example where we're going to use a table of integrals in our solution. Remember, there are lists of standard integrals in your booklets which are given in your exam. For example, we're going to be using this one in a moment, that the antiderivative with respect to u of 1 over a squared plus u squared is 1 over a times tan inverse of u over a plus c. Okay, so we're going to be using that as we go along. Okay, so here's our example. It says solve dy dx equals xy squared plus 4x given y equals 2 when x equals 1. Okay, so we're solving this differential equation. Xy squared plus 4x is equal to dy dx. So we'll start with that. And again, our first step is to find a general solution. Dy dx equals xy squared plus 4x. So our first step is to separate, which is challenging here. You know, I'm separating using the division or the multiplication properties. I can't just subtract that 4x from both sides, for example. I want to look for something I can divide. It's a bit of a problem, but what I'm going to do is I'm going to factor on the right hand side. So we're going to get dy dx is equal to, I'm going to factor out that x, and its factor pair is y squared plus 4. Now what I can do is divide on both sides by y squared plus 4, and at the same time I'm going to multiply on both sides by dx. Okay, so dividing on both sides by y squared plus 4, and at the same time multiplying on both sides by dx. Multiplying by dx on both sides will kind of eliminate this division over here and get me a dx over there. I'll have my x dx, which is what I want, and I'm going to divide on both sides by y squared plus 4, so that's going to kind of cancel that out from there and leave me with a 1 over y squared plus 4 dy over on the left hand side. Okay, so there's our first step, is to separate. So we've separated. We've got the y terms on the left with the y differential, and the x terms on the right with the x differential, and now I'm just going to integrate. Okay, so integrating. Now on the left hand side, I'll just remind you that we did look at this standard integral earlier on. So we're looking at this standard integral here. I have this standard integral 1 over y squared plus 4 with respect to y, and that's from your formula and tables booklets. If you go in there, you'll find at page 26 that's equal to, well, this is 1 over y squared plus 4. Y squared plus 4 is like a squared plus u squared. We're just going to have to be a little bit careful here. I'm just going to rewrite that so it looks like the integral. Now this is not necessarily taken from your tables. That's taken from the internet. It might have a slightly different layout for this thing, but I'm going to get this integral into this form here. So I'm getting my dy on the top, and on the bottom it's with respect to u here, so that's my variable. So I'm going to put my y squared as my second variable here. And then my first thing is some constant squared. So this 4 here I can write as 2 squared. So that's what I'm looking for. And the antiderivative of x with respect to x. And now I'm ready to apply my standard integral here. And so applying my standard integral, what I'm going to get, again, du over a squared plus u squared, that's just like dy over 2 squared plus y squared. So what I'm going to get is 1 over a, well that's going to be, a is 2 here in this case, so this is going to be 1 over 2, times tan inverse of u, the variable, over a, the constant. Well, y is the variable here, a is 2, so it's going to be y over 2. And then plus my constant of integration, which I'm going to put on the right hand side. The antiderivative of x is of course just x squared over 2, and then we're going to have that constant. Okay, so that's what we're looking at so far. That's kind of my general solution, if you like. At this stage, I'm going to address my conditions on my variables. So at this stage, I'm just going to address the fact that y is equal to 2 when x is equal to 1. So I'm going to address that fact now. So I'm going to say we're told that y has to equal to 2 when x is equal to 1. So solving here, we have 1/2 of tan inverse. That's 2/2. And that's going to equal to 1 squared over 2 plus c. So I've just substituted 1 in for x, and I've substituted 2 in for y. So I'm going to get 1/2 of tan inverse of 1 is equal to 1/2 plus c. Tan inverse of 1, well, that's something that you can do in your calculator. One thing I want to make sure to do is make sure that you're dealing with radian mode. It's important that we're dealing with radian mode here. So all of these differential equations, the angles are being measured in radians. And again, you should know what tan inverse of 1 is, of course. That's one of my special angles. So what I'm going to get is 1/2 of pi over 4. Tan inverse of 1 is pi over 4, or 45 degrees if I was dealing with degrees, but we're dealing with radians here always, and that's equal to 1/2 plus c. Okay, so we can see the constant of integration is going to be 1/2 of pi over 4, which is pi over 8, and then subtracting 1/2 from both sides, minus 1/2. Okay, so now I'm ready to write my particular solution. Therefore, 1/2 of tan inverse of y over 2 is equal to x squared over 2 plus the constant of integration, which is pi over 8, minus 1/2. Okay, so I want to see if I can solve for y here. I'm going to double both sides to get tan inverse of y over 2 is equal to x squared. Doubling pi over 8 will give me pi over 4. Doubling negative 1/2 is negative 1. If tan inverse of y over 2 is equal to this expression over here, well then y over 2 must be the tan of that expression. And now finally I'm just going to double both sides. So y is equal to twice tan of x squared plus pi over 4 minus 1. Okay. So twice tan x squared plus pi over 4 subtract 1. That's my particular solution to this particular problem. So again, don't forget that you've got lists of standard integrals in tables, forms in your booklets. So in this case, we had to rely on this particular standard integral. There's a number of them. You'll find them in there. I think it's on page 26 of your formula and tables booklets. Okay, so what did I do? First of all, factorized, then separated, then integrated using my standard integral. At that stage I applied my initial conditions to find the value of the constant of integration. Once I have my constant of integration, I have my particular solution, and then I made y the subject of the equation. Okay, so practice, practice, practice.